Bismillahirrahmanirrahim. Welcome to the 11th lecture of Discrete Structures CSC 102. In the previous lecture we have studied what is the rational numbers, what are the irrational numbers, and we have also seen that the real numbers are the union of rationals and irrational numbers. We have proved some properties of rational numbers and demonstrated some theorems related to rational and irrational numbers. We have studied also absolute values, triangular inequality, and we have also discussed the floor and ceiling functions. Today we are going to discuss some properties of floor and ceiling functions. So today and also today we shall start the methods of proof. In that we will start by direct methods. We have studied the definition of floor and ceiling function in the previous lecture, and now we consider some examples how we apply the floor and ceiling functions on the real numbers. For example, you can see on the slide that if we take 25 by 4, what is the floor and ceiling of 25 by 4? If we simplify 25 by 4, if we perform the division, we obtain 6.25 in decimal form. So now 6.5 is greater than or equal to, here we must write greater than or equal to by the definition of floor function. So 6.25 is greater than or equal to 6 and less than 7. So by the definition of floor function, what will be the floor of 6.25? 6.25. The floor of 25 by 4 or 6.25 will be 6, as we see in the definition that the floor of any real number is the immediate less integer of that number. So the floor of 25 by 4 is 6, and the ceiling of 25 by 4 is basically 6 less than 6.25 less than or equal to 7, as we have seen that in the ceiling function the equality comes here, but in the floor function the equality comes here, and the ceiling of any real number is the immediate greater integer of that number. So the ceiling of 6.25 will be 7. So I hope you understand how we can calculate the floor and ceiling of any real number. The remaining two examples we can see also. For example, the example C, minus 2.01. What is the immediate less integer? Here for floor we write less than or equal to, equality comes here, and for the ceiling equality comes on the other side. For the floor function of this minus 2.01, the immediate less integer is minus 3. So the floor of minus 2.01 is minus 3, and ceiling of minus 2.01 is minus 2, because it is immediate greater integer of minus 2.01. So this is a little revision of this floor and ceiling functions, how we take the for any real number, what is the floor of that number and what is the ceiling of that number. So next we take a simple daily life example in which we can apply floor and ceiling functions. So if we suppose that there are 1,370 students at a college, and they want to go out for a visit, out for a game, anything. We have 1,370 students, and each they will go out for a game out of the town to play a game, for example cricket, football, anything. And in college there are buses which will take them to the game place, wherever the ground is. Each bus has a capacity of 40 passengers, means 40 students, 40 passengers can sit in the bus. And the college principal or the institute director, he says that for reasons of economy, the athletic director means whoever is their game director will send only full buses for the reason of economy. For example, that to save money, the athletic director decides that no bus will go empty or half full bus, means there will not be empty seats in a bus. So what is the maximum number of buses the athletic director will send? So athletic director doesn't allow that bus to go which is not full of passengers. Full of passengers means the bus in which there are not 40 passengers. So how we can calculate that? We have 1370 students and each bus have capacity of 40 passengers. Then how many buses will go out of the town for game? So we divide simply 1370 by 40 and we take the floor of this number. 1370 divided by 40 is basically 34.25. What does it mean? That 34 buses will be full, and 0.25 expresses that some of the students, less than 40 students, will sit another bus which will not be full, and that the director will not allow to send out of the town for game. So therefore we have to take here the floor of this number. So if we take the floor of this number, we can easily calculate that floor of 34.25 is 34. So the director will send 34 buses which will be full with 40 passengers in each bus. So obviously there will be students which will be left, and they will not be able to go out of town for game. So in the second part of this example, if the athletic director is willing to send one partially filled bus, means in part A, as we have seen that there were some students who were left behind and they couldn't go to play the game. Now the second condition, in some other occasion, the director allow that he will send all the students to play a game. How many buses will they need to send all the students, in which one bus will be partially filled? So we need to tell how many buses will be needed to allow all students to take to the trip. So in this case, we do not restrict the number of students, number of passengers. We need to calculate how many buses they need to take all students to the playground or whatever, wherever they want to go. So here we take ceiling of 1370 divided by 40. So 1370 divided by 40 is 34.25, again the same, but here we take the ceiling of this number. So we can calculate easily that the ceiling of this number is 35. So 35 buses will be needed to take all the students to the playground or to the ground where they want to play that game. So this is how we can apply ceiling and floor functions in daily life problems and daily life problems of such kind to calculate the complete integers such that 34 and 35. So next we study some properties of the integer. If k is an integer where floor of k and floor of k plus 1 by 2, both these floor functions will give us same value. Why? Because now we can see the solution in detail. Suppose k is an integer, then the floor of k is will remain k, because k is itself an integer. If we have an integer, then the floor of that integer will remain same, because the immediate less than or equal to that number integer will be the same integer. By the definition of floor, we can see that the floor of k is k. Now, the floor of k plus 1 by 2, what will this expression will give us? Now k is integer. Now this also give us the value k. Why? Because k is an integer, and k plus 2, the immediate less integer than k plus 2 will be k, because here k is integer, we add half number, 0.5. For example, if we have 5 here, 5, here we have 5, here we have 6, here we have 5.5. The immediate less integer than 5.5 remains the same, 5. Here we have 6. So in both cases, in this case and in this case, the answer remains same. So the floor of k, if k is integer, and the floor of k plus 1 by 2 will be the same integer. Another property which we shall disprove with respect to the floor of any two real numbers, that floor of x plus y, we have to prove that this statement is false. Floor of x plus y is not equal to floor of x plus floor of y. We have to prove this statement, which is written that floor of x plus y is equal to floor of x plus floor of y. This statement is false in general. So there are several methods of proving statements. We shall discuss these methods in when we study the methods of proof. But here for this statement, we shall disprove it by giving some counterexample, as we have studied already that universal statements can be disproved by using a counterexample. We have seen what do we mean by counterexample in the previous lectures. The statement is false. This statement is generally false if we take x, y 1 by 2, both x and y 1 by 2. Then if we sum up x plus y, it will become 1 by 2, 1 by 2 and 1. The floor of 1 will give us 1. Now if we take floor of 1 by 2, floor of 1 by 2, floor of 1 by 2 is 0 by the definition of floor function, and the floor of this 1 by 2 is also 0. So this 0 plus 0 is 0. Now 1 is not equal to 0. So in general, this statement is not true. Why? Because these are basically universal statements. For all x, y, we write this. Therefore, we have seen that by giving a counterexample, the given statement is not true for this example. Therefore, we can conclude that this general statement or universal statement is false. Another property of the floor function is that for all numbers x and all integers m, we have floor of x plus m is equal to floor of x plus m. Means floor of x plus m is equal to floor of x plus m. So these two things are different. So here m is integer and x is real. X is real and m is integer. So we see that we have already seen that the floor of an integer is the same integer. So the floor, if we apply floor on a real number plus integer, then the floor will not be applied on this integer and this will remain the same, but the floor will be applied on only on x. So this is basically the idea in this property. Suppose how we prove it. Suppose a real number x and integer m are given. Then we suppose that floor of x is n. Floor of x, by definition, it will give us some integer which is immediate less integer than x. So that unique integer n such that now n is less than or equal to x less than n plus 1. This is by definition of floor function. Now if we add up m on both sides, m we added on this side, we added this on this side, and m we added on the right hand side. Now if we see by definition x plus m, what is x plus m? This is a real number. This is greater than or equal to n plus m less than n plus m plus 1. This is what? This is basically the definition of floor function. So from this inequality we can write floor of x plus m is equal to n plus m. So this, here we have used the definition of floor function, but here we have said that n is equal to floor of x. So instead of n here we can write floor of x. So this we have proved equal to this, which was required to prove. So we can prove that if the floor of a real number plus an integer, this is same as we take the floor of that real number and integer we write as it. So this was another theorem related to the floor and ceiling functions, floor of functions. Another theorem related to the floor of real numbers. If we take any integer n, then the floor of n by 2 is equal to n by 2 if n is even, and n minus 1 by 2 if n is odd. So we have to prove this. So there are two cases. If n is an integer, then there are two cases. Either this integer is odd or this integer is even. There are only two possibilities for the integers. Either integers are even or integers are odd. So we discuss both cases here. First we take suppose that n is an odd integer. We take n as the odd integer and we write it as 2k plus 1, because any odd integer can be written in the form of 2k plus 1 for some integers, for some integer k. Now n by 2 can be, floor of n by 2 can be written as 2k plus 1 by divided by 2. Now if we separate these terms, this becomes 2k by 2 plus 1 by 2. So what is this? Basically 2 cancels with each other and we obtain k plus 1 by 2, and we have seen in the previous slides that k plus 1 by 2, if k is integer, as we have mentioned here that k is integer, and we add up 1 by 2 in this integer, the floor of this k plus 1 by 2 will be k. So now what is k? Here we have n is equal to 2k plus 1. If we take the value of, if we find the value of k here, this will be n minus 1 divided by 2, n minus 1 divided by 2. So here we have floor of n by 2. This is equal to k, and what is k? K is n minus 1 by 2. So k is equal to n minus 1 by 2. So the floor of n by 2 becomes what? N minus 1 by 2. So which was required in this case when n is odd. Now we shall prove for if n is even. In this case n is 2k, and for some integer k, n by 2, where n is 2k, here 2 cancels with 2 and we have obtained k. Floor of k is k because k is integer. So what is here? From here we can find the value of k. N is 2k and k is what? This is n by 2. So floor of n by 2, we have proved here that this is equal to k, but k is n by 2. So therefore the floor of n by 2 remains n by 2 if n is even integer. Therefore we have proved this theorem for any integer n. The floor of n by 2 will be n by 2 if n is even, and n minus 1 by 2 if n is odd. So next we start now the methods of proof. What is the proof? First we should know this, that what is proof, and then we shall discuss methods of proof. A proof is a logical structured argument which demonstrates that a certain proposition is true. So when the proof is complete, the resulting proposition or any statement which we are going to prove becomes a theorem. This we call as a theorem. Means if we want to prove any statement, any universal statement or proposition to be true, then its proof will be a logically structured argument. Logically structured arguments that we use previously established results in mathematics to prove that the given statement is true with a logical structure, step-by-step arguments. And this type of logically structured arguments are called a theorem if the given statement is rather simple or it is a short proof. Then we can call it a lemma. Lemma actually is a short result which is used to, or which is required to prove bigger or larger results, which are usually called theorems. Now we know what is a proof. Now we are going to discuss the methods of proof. There are usually, if we divide in broad cases, there are two types of proofs: direct proofs and indirect proofs. And in indirect proofs there are several methods which we will study here, but first we see what is the direct proof and what is the method of proving a proposition or a theorem directly. There are three major steps in direct proofs. The first step is express the statement to be proved in the form universal statement. This is basically universal conditional statement, as we have studied in logic. For all x belongs to D, where D is the domain, we have studied in logic. D is the domain. This P of x is basically called hypothesis, and Q of x is called what? Conclusion. So first of all, we shall convert the given statement into the universal conditional statement. That is, for all x belongs to domain, if the hypothesis is true, then the conclusion is true. Then how we prove it? In the second step, we start the proof by supposing x is a particular but arbitrarily chosen element of D, for which the hypothesis is true. We suppose basically the hypothesis of the given statement is true. We suppose it, and we then in the third step prove that the conclusion is true by using some already established results, theorems, lemmas, results in mathematics. So what is the general method of direct proofs? It involves three steps. The first step is that first we identify hypothesis and conclusion, and we write the given statement in the form of universal conditional statement. That is, for all x belongs to some domain, we suppose that P of x is true, and we prove the conclusion Q of x is true. We see the whole process by considering an example of the proof. For example, we have to prove this statement: the sum of two even integers is even integer. That is, if we add up to any two integers, even integers, if we add up any two even integer, the result will also be a even integer. So according to the broad method of the direct proof, first of all, we shall try to write the given statement into universal conditional statement. So we write it as, for all mn belongs to z, means for any two integers, if m, n are even, then m plus n is even. So this is how we can translate the given statement into a universal conditional statement. This basically, this steps comes into the deconstruct axioms. This basically, the first step in the method of direct proof is called deconstruct axiom. The second step is basically called mathematical insight, and third step here, this is basically called reconstruct conclusion. So these are three basic steps in direct proof in the language of logic. So the first step here is deconstruct axiom. If we take up this step in more detail, then first of all, in this step, deconstruct axiom, we write the given statement into universal conditional statement, and then I explain it here on the next slide, take the hypothesis and turn it into a usable form. And usually this amounts to just applying the definition. For example, in this statement, we have supposed for all x belongs to D, if P of x. If P of x means if the hypothesis is true. For example, in this step, deconstruct axioms, we suppose that the hypothesis is true, and we convert it to a usable form by using the definition of P of x, as the P of x is given here. We use the definition here. If m and n are even integers, so by definition of even integer, what will be the deconstruct axioms? In this, we suppose that we have two even integers, m and n, and by definition of even integer, we can write m as 2r and n as 2s, where r and s are any other integers. So this is, we can write it m and n in the form of even integers 2r and 2s. So this, here we have turned the hypothesis into usable form. So this is basically the deconstruct axiom. Now the second step is mathematical insight. Now in the second step, what we do, we use human intellect, we use our brain and get a real reason behind theorem. And in the second step is basically the main step in which we think, we stress on our mind that how we can prove the conclusion on the basis of some logical results, logical you can say expressions, or already mathematical established results. In this part, we think how we can prove. For example, in this theorem, we have two even integers now in the first step, and now we are going to prove that sum of these two integers will also be even. Now what we think in the second step, that how we can prove it, in this step we add up the two even integers. For example, m plus n. If we add up m plus n, we can write m plus n as 2r and 2s. Now we also think that how we can prove that the resulting integer is also an even integer. The resulting integer is basically m plus n. So how we can prove it? Now what is the definition of even integer? I think in the third step, to obtain to reach at some certain conclusion, we have to prove that sum of these two integers, even integer, will also be even. So if we take up sum and we think how we can prove it, and we remind the definition of even integer, that if we can multiply any integer by 2, then it will become even. So from here we take, in this step, from here we take 2 common, and r is integer, s is an integer. Sum of two integer is integer, and this integer is multiplied by 2. So this becomes also an even integer. So this is even integer, this is even integer. If we take up sum, the resulting integer is also an even integer. So this is what we have proved in third step. So this was what required in the given statement, so the theorem is complete now. This is how we think in proving theorems or statements or propositions directly. So the first step is basically, I repeat, deconstruct axioms. In this we suppose that hypothesis is true and we turn the hypothesis into usable form. And in second step we think we think about the real reason, how we can prove, how we can proceed towards the conclusion by using some already established results in mathematics. And at the end we see what is the definition of conclusion, and we apply whether we have reached on the conclusion or not. So this is basically the process of proving a given proposition by direct method. I have summarized the last theorem which we have proved here. This is given in the book of Discrete mathematics written by Susanna. So the sum of any two even integers is even. So suppose in this proof in the book he didn't explain all the steps, but the steps behind the direct method of proof are the same, which are construct axioms, mathematical insights, and reconstruct conclusion. There is no need to separate these steps, so you just think these steps in your minds and you proceed the proof. Suppose M and N are even integers. By the definition we have converted the hypothesis into usable form, and in the second step we add up these two integers and we apply the definition of even integers and we construct the result, and we have the result. So this is how we can prove the theorems or any statements or propositions. We can provide proof by direct methods. We consider now a disproving by counterexample. If you think that this statement, the given statement, any given statement cannot be proved by direct method, then what we do? We try to disprove it. For example, if we give a statement like this: for all real numbers a and b, if a square is equal to b square, then a is equal to b. We cannot prove this statement because this statement is not always true. If you are sorry if you are unable to prove this statement by direct method, then there must be some problem in this statement. So we try to disprove this statement by using some particular example. So how we disprove a statement? By giving a counterexample. What is counterexample? We have already studied it. To disprove a statement of the form, the universal conditional statement for all x belongs to D, if P of x then Q of x, we try to find a value of x in D, in the domain, particular domain which is given here, for which the hypothesis is true, but the conclusion is false. We try to find some particular value of x for which the hypothesis is true, but the conclusion is false. This is what we have studied in conditional statements, that P implies P implication Q when this statement is false, when P is true and Q is false. So the whole statement becomes false if P is true and Q is false. So the whole statement becomes false. So this is what we are going to prove here in disproving the statements or propositions by giving counterexample. Counterexample is a particular example, you can say. So we are going to disprove this statement, which is written in the universal conditional form, because here we have for all, here we have domain for all real numbers a, b, if this is a domain, and this is if, this is p of x, and this is q of x, this is q of x. So we are going to find some particular real numbers for which a square is equal to b square, but a is not equal to b. This is what we have to prove, or we have to demonstrate in such type of disproving by counterexample. So this is a very simple example. We can take the value of a is equal to 1, b is equal to minus 1. So we can see that 1 square and minus 1 square are both 1, but this doesn't imply that 1 is equal to minus 1. So this is a very simple example of this statement, the counterexample, which disprove this universal conditional statement. So this is a method in which we can disprove the given universal conditional statement, or any statement we can disprove by giving some particular example, which is called the counterexample. There are many other counterexamples. For example, if we take a is equal to 2, b is equal to minus 2, a is equal to 3, b is equal to minus 3. So all these examples are the counterexample for this statement. So this is how we can disprove universal conditional statement to be false if we are unable to prove it by direct method of proof. Consider another example here. For all integers a and b, if a divides b and b divides a, then a is equal to b. So division we have studied in the previous lecture. If a divides b and b divides a, then a is equal to b. So this is a theorem, this is a statement, and we have to prove it. You can try. We are unable to prove this statement by using direct methods of proof. So what we do, we try to find some particular example, a counterexample, which disproves the given statement. So we look for two integers a and b which divides each other, but they are not equal. So we can take the same examples as we have taken in the previous case here. Here if we take a is equal to 2, b is equal to minus 2. Now 2 divides minus 2 and 2 divides minus 2 and minus 2 divides 2, but 2 is not, but this doesn't imply 2 is equal to 2, that is 2 is not equal to minus 2. So the given statement is wrong, because we have given a counterexample, a particular example which disproves the given statement. So this is how we can prove a given proposition or given statement false by giving some counterexample. Next we see what the proof by contradiction. So this is also a direct method of proof. So what are the major results in the proof by contradiction? The first step is basically suppose, as by the name contradiction, we suppose that the conclusion is false. This is a method of proving a statement. Basically, to prove a given universal conditional statement, we suppose that the hypothesis is true, and we have to prove the conclusion is also true. Now in this method we suppose that the conclusion is false. We are supposing that is, we suppose that the negation of the statement is true. Now next we show that this supposition leads to a logical contradiction. By using some already mathematical established results, we proceed on the same steps, and we prove at the end that what we have supposed is basically wrong, and if we are able to prove that what we have supposed, which is basically wrong, then what will be true? The negation of this is true, that is, the conclusion will be true. So this is the method of proving a statement by contradiction. We study this method by considering an example. So this is a given statement which we have to prove. There is no integer that is both even and odd. So we proceed on the same steps. First we as we have studied in the direct method, that is, first we deconstruct axioms, then the second step is mathematical insight, third step is reconstruct conclusion. We do usually the proof like this, but here now I am writing in general the proof. That is basically deconstruct axiom, mathematical insight, and the third step. This basically goes only you think in your mind. So first of all, the given statement, how we can write it, how we can write in universal conditional statement. There is no integer that is both even and odd. What does it mean? For all integers m and n, m is, you can say, even, and m is odd. So we take the negation of theorem and suppose it to be true. Suppose not, that is, there is an integer. So in the method of contradiction, we suppose that here, as this is mentioned, suppose that the statement to be proved is false. That is, suppose that the negation of the statement is true. So what is the negation of this statement? We suppose that there is an integer which is both even and odd. This is the negation of the given statement. So suppose not here, that is, suppose there is at least one integer n that is both even and odd. So we have supposed the negation of the given statement. So we must deduce a contradiction. Now by giving some logical expression, by using some already existing mathematical results, we shall prove that what we have supposed is not true. That is, what we have supposed is a contradiction. So what we will conclude that the given statement is true. So this is basically the method of contradiction. So by the definition of even number, here we have supposed that there is at least one integer n that is both even and odd. So if integer n is even, then it can be written as 2a, where a is some other integer. A belongs to z. If n is even integer, now we have supposed that n is at the same time odd also. N is even and n is also the odd integer. So n can also be written as 2b plus 1, where b is some other integer. Now n has two representations. N is even also, n is odd also. N is equal to 2a, n is equal to 2b plus 1. Here left hand sides n and are equal, so right hand side must also be equal. So 2a is equal to 2b plus 1. So if we take 2b on other side, 2a minus 2b is equal to 1, and we take the common 2 into a minus b is equal to 1. So a minus b is equal to 1 by 2. So we have used some already existing results in mathematics. So now since a is integer, as we have supposed here, a is integer, b is integer, and we know that the sum of two integers is integer, sum or subtraction. If we take a plus minus b, we can say that sum of two integers. Sum of two integers, we have proved already by using direct method that sum of two integer, no, that we have proved sum of two even integers. Here we have sum of two integers. We know that sum of two integer is also an integer. So here a minus b is also an integer, but here we have 1 by 2, which is not an integer. What is this? This is basically a rational number. So left hand side we have integer, right hand side we have rational number. So a minus b must be an integer, not the rational number. We have proved that every integer is a rational, but not every rational is an integer. So therefore we can see that this is a contradiction, because on left hand side we must have integer, on the right hand side basically a minus b must be integer by the definition, but here we have a minus b comes rational. So this is basically not possible, or we can say that this is a contradiction to the fact that we have supposed a is integer, b is integer. So the difference must also be integer, but difference is a rational, which is not an integer, thus ab is integer and ab is not an integer, which is a contradiction. So we have two possibilities. Here we have a minus b is rational, and by seeing these suppositions, the a minus b must be integer. So what is true? We are not sure. That this is basically a contradiction to the fact that which we have supposed. We have supposed that there exists some integer which is both and even and odd. So if we are arrived at a contradiction, then what we say that our supposition was wrong. What was our supposition? That there exists some integer which is both even and odd. So this supposition is wrong. Then what is true? The given statement is true. So we have proved the given statement by using the contradiction method. So this is basically the method of contradiction. We take another example, this, or another example. This is a very simple example. So we take this. The square of an even number is even. So this we have to prove. The square of an even number, if we take an even number, for example 4, then its square is also square is 16. If this is even, this must also be even. This is what we have to prove. So to prove this statement by the method of contradiction, what we say, we suppose that there is an integer, there is an even integer whose square is not even. So we suppose the negation of the given statement is true. What is the negation of the given statement? The given statement is the square of an even number is even. So the negation of this statement is the square of even number is not even. So this is the negation. So we suppose that, suppose k is an even integer and its square, k square is not even. We suppose it. Now we shall prove this statement wrong. Then we say that our supposition is wrong and we arrive at some contradiction, therefore the given statement is true by using the method of contradiction. Suppose k square is, if k square is not even, then k square must be odd. So we say that k square is odd. If k square is odd, then there exists some integer n such that k square can be written as 2n plus 1, where n is what? N is integer. So if k square is equal to 2n plus 1, then we can write k square minus 1 is equal to 2n. That is simple. We factors k square minus 1. How we can factor it? K minus 1, k plus 1 is equal to 2n. So how we factor, we have already, I hope you have already studied this formula, a square minus b square is equal to a minus b into a plus b. This is how we can factor k square minus 1. Now k minus 1 into k plus 1 is equal to 2n. What does it mean? It means 2 divides k minus 1 into k plus 1. It means 2 divides k minus 1 k plus 1 by using the definition of divisibility we have studied in previous lecture. If 2 divides k minus 1 into k plus 1, it means either 2 divides k minus 1 or 2 divides k plus 1. And since 2 is prime, then there exists k minus 1 is equal to 2a. Means if 2 divides k minus 1, by the definition of divisibility, we can write k minus 1 is equal to 2 into some as the divisor d, 2a, where a is some integer. Or if 2 divides k plus 1, then k plus 1 can be written as 2b. b is some other integer. So here, from here we can write k is equal to 2a plus 1. From here we can write k is equal to 2b minus 1. So what does it mean? K is equal to 2a plus 1, k is equal to 2b minus 1, where a and b are some integers. It means that k, in this case, k is odd. In this case, k is also odd, because 2a plus 1 is odd number and 2b minus 1 is also an odd number. So here we have, in both cases, k is odd. So k is not even. But we have concluded here that k is not even, k is odd. We have proved here, which is a contradiction. Why it is a contradiction? Because we have supposed that k is an even integer. We have supposed that k is an even integer, but its square is not even. So here we have arrived at k is not even, which is contradiction to the supposition. This here we have that k is not even, here we have that k is an even. So these two statements are contradictory in this proof. So we arrive at a contradiction. Therefore we say that our supposition, what we have supposed, that k square is not even, is wrong. If this supposition is wrong, then what will be true? K square will be even. This statement is true. So we have proved by method of contradiction that the square of an even number is even. So this is basically the proof by the method of contradiction. We can similarly prove this theorem also. The sum of any rational and any irrational is irrational. This theorem we can also prove by the method of contradiction. The sum of any rational number and any irrational number is irrational number. So we take the negation of, on the same process, take the negation of this statement that the sum of rational and irrational is not irrational. We suppose that is not irrational, then it will be rational. So by taking some other steps, you see in this proof. This proof is also given in the book of Discrete Mathematics by Susanna. You study this proof. I hope you will understand this proof. And for today, and we stop here. In the next lecture, we shall discuss the indirect methods of proof, and we shall revise some of the direct proofs also, and in detail we shall discuss the indirect proofs. So what we have studied today, we have studied some properties of floor and ceiling functions. We have proved some theorems related to the floor and ceiling functions. We have started today the methods of proofs. I have told you that there are two major branches of methods of proof: direct methods and indirect methods. In direct methods, we have studied two methods: direct method and the proof by counterexample, and disproving a statement by giving some counterexample. And we have studied also the method of contradiction in direct proofs. In the next lecture, we shall start the indirect proofs. Thank you very much. Allah Hafiz.